So this is our general full device view. We start out with our inputs that go through an ALU. That ALU's value gets spit into the decoder, and then the decoder determines what to display on the display. And we also have LED down here as our warning indicator for the temperature.
In order to get our temperature data from the onboard chip, we need to use I2C communication, which utilizes a 200 kilohertz clock. On board, we have available a 100 megahertz clock, which you see here and is given in our constraints folder. But this must be converted to 200 kilohertz to enable that communication. This is all done via code we found online because it was in our best interest to not try and reinvent the wheel for this step, as well as the I2C communication, which is found here. Links are all in our README file. The I2C file essentially uses that 200 kilohertz clock, an SCL and an SDA wire connection, to send data between the board and the temperature chip. It does this using an SDA direction pin, which is defined at the bottom, and essentially tells you which direction data is flowing from. For our purposes, the data is mainly flowing from the pin from the chip to the board, so this isn't something we're overly concerned with.
So once we get that temperature, we use that module in the ALU, and in the ALU we have the same 14 operations as before, except now we replace the final two with getting a temperature in Celsius and getting a temperature in Kelvin. And so this value gets sent to the decoder, which displays the number on the 7-segment display. So the way this works is we have an input clock, which comes from the FPGA, and we use that clock down here to constantly iterate a refresh counter. And using that refresh counter, we can constantly check what number from the final 2 bits we want to use, and with that we activate a different anode, which represents a different numbers place. And then we set the LED BCD, which just outputs the 7-segment display cathode value from the digit. And we basically just constantly refresh this, displaying one number at a time very fast, so that we can get a perceived 4 digits displayed on the display. And towards the end, we have our warning out, which just checks if our input value is greater than a specific value. If it is, then we just set the warning out indicator to 1.
Do you need me to touch it?
Yes.
So we wanted to do something similar to the EK131 temperature box problem, where you have ambient room temperature and you have some set threshold for it. And if the room was to get too hot, it would alert the user of that danger. And we figured this is all like digital logic design, so we wanted to create an implementation of that using hardware rather than using software with an Arduino.
And more specifically with the temperature, it utilizes an I2C protocol, which is something we are not too familiar with before this. So we wanted to work with temperature off the board to work with I2C.
Yeah, we figured it's pretty applicable in a lot of scenarios and could be used in CAN communication, which is something we do for other clubs. So we thought this was a great time to kind of experiment with networking.
So a lot of the struggles I had were just keeping track of bit sizes, to be honest, and also trying to work with the 7-segment display to get it to display all the numbers at once instead of just one number at a time.
Yeah, I noticed working with the clock and the I2C communications, it was pretty difficult to try and navigate the protocol and just actually implementing it. So it was easy on paper, but definitely harder to implement.